Welcome everyone. Group B is here to present to you a tutorial on machine learning, both at the theory and practical level. So to give you an overview on what machine learning really is, it is important to note that it is merely a subset of AI. In the simplest manner, machine learning is the practice of using algorithms to parse data, learn from it, and then make a determination or prediction about something in the world. To drill down even further, deep learning is a subset of machine learning which is concerned with algorithms inspired by the structure and function of the brain called artificial neural networks. It is what's behind driverless cars, enabling them to recognize a stop sign or to distinguish a pedestrian from a lamppost. So what's the difference? In deep learning, a computer model learns to perform classification tasks automatically and directly from images, text, or sound. A key advantage of deep learning models is that they can achieve state-of-the-art accuracy, sometimes exceeding human-level performance. Also, interestingly, they often continue to improve as the size of your data increases. On the other hand, with machine learning, you manually choose features and the classifier to sort images. For the machine learning process, we can think of it with the following 5 steps. The first step of feature transformation is critical for data pre-processing, and it is when a set of new features are created. Now we'd like to apply this using the scikit-learn library as an example. It is an open source library which was released in 2007 and covers various machine learning algorithms. It is known for being user-friendly, but one of the key downsides is that it's not equipped to perform advanced statistical programming. Some of its key use cases include predicting customer churn and text classification, and companies who have used scikit-learn include Spotify and Booking.com. Data preprocessing is critical in order to transform raw data into understandable format before feeding it to the algorithm. This can be done through a variety of techniques such as scaling, so that variables can be compared on common grounds and is performed on continuous variables, through standardizing, where features are rescaled to have the properties of a standard normal distribution, and through encoding, to turn categorical variables into numeric values, as well as binarizing, which thresholds numerical features to get Boolean values. The good news is that all those techniques can be used from the sklearn preprocessing package, which is pre-built in scikit-learn. In this example, we first import a dataset, which in this case is on automobiles, and we load pandas and numpy as supporting libraries, and we define our own headers. Before kicking in scikit-learn, we can use the selectDtypes function in pandas to build a new data frame containing only the object columns. This is important since we are only focusing on encoding categorical variables. Then to do a label encoding on the make of the car, we need to instantiate a label encoder object and fit transform the data. As you can see, the text attribute of the make of the car was turned into numerical values. Using scikit-learn, we can also do binary encoding by using the label binarizer. After a dataset is pre-processed, a next step in the machine learning process is feature selection. In the simplest form, this means that a subset of the data with relevant features is used and fed into the model selection process. It can help reduce the risk of overfitting. Next in the process is model selection, which is where we need to select from the handful of machine learning algorithms. Machine learning algorithms can be broken down under 3 main categories: supervised, unsupervised, and reinforcement learning. As you can see, the main difference is that supervised learning helps predict outcomes. Unsupervised learning finds hidden structure and patterns in your data, whereas reinforcement learning is reward-based. For this next example, we will be looking at 2 libraries which have been developed by Facebook. PyTorch is a new library which was only released in 2017, and although it performs machine learning algorithms, it is known for being a deep learning library. It's gaining large traction due to its flexibility and simple interface. However, the fact that it is still new, there is therefore not much community support as of yet. Notable companies such as Twitter and Salesforce use PyTorch. Some of its key use cases include image classification and natural language processing. On the other hand, Caffe2 is the successor of the Caffe library, and although it was also released in 2017, the deep learning library is only used in production environments. It is more lightweight than PyTorch and will actually be integrated into the PyTorch 1.0 version. We have taken up a linear regression model with one feature that can be optimized using a gradient descent technique leveraging PyTorch. The data considered visually looks like this when plotted using Seaborn. Now this graph shows the predicted line before optimization, and as you can see, the line is far from the best fit. We then run a series of training steps using a utility function leveraging gradients. Then we plot the linear regression after optimization to display the real versus predicted results. The fit line proves that it keeps moving closer to the desired fit line. Now for the other library by Facebook, which is Caffe2, we will perform an example of image classification using a pre-trained model. First, we would need to import the required modules and specify the required inputs. The image preprocessing then takes place for ingestion into a Caffe2 convolutional neural network through the rescaling method. Here we can see the result output. Once that is done, the convolutional neural network, otherwise known as CNN, is prepared and the predictions are initiated from the input protobufs and consequently evaluated by the confidence. Based on the findings, the model predicted code 951 with a confidence of approximately 95%. After cross-checking the result against the list of image codes, we can verify that the classifier is working since code 951 is in fact a lemon. Two other notable libraries in the deep learning space are TensorFlow and Keras, which are both developed by Google. TensorFlow was initially intended for internal use but was then released in 2015. Despite its complexity and lack of computational speed, it is widely adopted by companies such as Uber and Airbnb due to its flexibility to execute on multiple platforms, its performance, community engagement, and highly modular architecture. A sample use case is Google Translate for speech recognition. The other library, Keras, was released in 2015, and similarly to PyTorch, it is also gaining popularity among companies such as Netflix and Yelp due to its ease of use, simplicity, and its ability to foster rapid prototyping. You can see from the below example the simplicity in the Keras code versus the TensorFlow code of 5 lines. And this, in turn, explains the large volume of Keras usage in Kaggle forms in comparison to TensorFlow. If we look at the deep learning framework PowerScores from 2018, we see the order of TensorFlow, Keras, PyTorch, and then Caffe2. Scikit-learn is not on this graph as it focuses on machine learning techniques. Now, for a practical deep learning example, we would like to show how Keras and TensorFlow can be used in a complementary way for image classification, where Keras is used in the front end and TensorFlow is used as a back-end engine. The example is related to a convolutional neural network model for image classification on fashion apparel. The MNIST database is used for this example as it is a large database of handwritten digits which is often used for machine learning algorithms and training various image processing systems. So after the train and test data from the fashion MNIST is loaded, the text description of the apparel is then labeled. As part of the pre-processing step, we normalize the data dimensions so that they appear to be the same scale. Then the data is split into 3 sets: train, test, and validation, and we perform one-hot encoding on the labels to convert numeric into categorical variables. Now it's time to see the power of the deep learning libraries by creating the model. So we define the input shape in the first layer of the neural network and verify by running the summary of the model. The model is then compiled using model.compile, as this helps configure the learning process before the training takes place. The type of loss function, optimizer, and metrics to be evaluated by the model are identified. Keras library is then used to train the model using model checkpoint. Then it is passed to the training process when calling the fit function on the model. The model is then evaluated using the test set. As we can see, the test accuracy score is quite high, showing 91%. It is always good to visualize our data. So in this case, we are visualizing our predictions. and we can see that the predicted results are showing as green, meaning that they are true. The last two steps in the machine learning process are feature validation and metrics. Although we did just cover an evaluation technique with the previous fashion image classification example using Keras and TensorFlow, there are other methods to consider apart from accuracy score. Typically, after a model is selected, we will need to evaluate its performance using certain metrics. For example, with a simple linear regression, we can focus on 3 key metrics for evaluation: the mean squared error, the mean absolute error, and the R-squared. So let's say if we use scikit-learn to plot a linear model, we import the regression metrics and run the code. Both mean absolute error and mean squared error are often used in predictive modeling. The R-squared suggests the goodness of fit of the model, which ranges between 0 and 1. The metric here suggests that we have a good fit. Now we've reached the point where we have observed the whole machine learning process, which was supported with some theory, business context, as well as with some practical examples of Python code for each of the libraries. Thank you for watching our machine learning tutorial.